Hello, today we'll discuss about density of state. Suppose for a classical ideal gas, if I change its energy from E to E plus dE, what will be the change in the available energy state of the system? So this number of state change is directly proportional to the amount of energy change, and the proportionality constant is called the density of state, and that is what we are going to derive for a classical ideal gas. So the number of state can be obtained in terms of the phase space volume. This is the change in phase space volume that corresponds to the change of energy of this much. So if you divide this phase space volume by the volume of one microstate, one will get the total number of microstate, that is nothing but the total change in volume for the change of energy of d epsilon. So we know for a classical ideal gas, energy depends only on the momentum coordinate and it independence of spatial coordinate. So this can be replaced by the total volume of the system V, and what remains is d cube of P. This d cube of P is nothing but the volume of small spherical cell in momentum coordinate, and this actually d cube of P is the small volume of annulus region. So that can be found on once if you know the surface area of the inner cell, which has the radius P and the length of this this annulus region, that is dp. So surface area of the inner cell is 4 pi p square and the length is dp. Multiplying this to one will get the d cube of p, and substituting for p squared from equation 3, and dp can be obtained by differentiating p with respect to epsilon. So this is your dp. Substituting equation 6 and 8 into equation 4, one will get the expression for density of state, and simplifying this one will get the density of state expression for classical ideal gas that obeys this dispersion relation.